Alrighty, so then let's welcome back for the second half of the course, basically. So today we're gonna talk about more like the game we played, how we can hack it, and to get a better understanding of how you can trick these sorts of AIs, for example, in drawings, and we will get a better understanding of what it means to do adversarial attacks. Obviously, now we are also going a bit more into the direction of hacking. And I guess when you talk about hacking, then maybe most of you, or the most people, they think like, okay, hackers are bad people or like they do malicious stuff. But in fact, we have different kinds of hackers or hacking techniques. The black hat hackers or the black hats, they are obviously the bad guys. But for example, we also have the white hackers and the gray hackers, and they are somehow in between. That's what I like, for example, are red hackers. They're gonna try to hack back. That's quite interesting. So there are also hackers that try to hack hackers. And but what we do here in this course is a more like, I would say, like green hacking. So it's literally more like how to learn or learning hacking. But again, right, for example, big companies, what they do is they have a system and then they hire hackers to get into their system to detect how secure the system is. And these are, for example, red hackers. And of course, there are also people who do that like just for fun. And then when they found something, they basically report that to the institute and say like, hey, look, I found something. If they're lucky, they get paid. If not, there are also quite interesting examples. For example, there was a hacker, she found out a bug in an application by the CDU in Germany like 2 years ago. She reported it to the party and they sued her because there's a weird aspect in, I think it's German or maybe Europe, I think it's probably German law, which is means basically like if you find a backdoor or some malicious part in a software, unfortunately, a lot of people, they don't report that because in fact it means that you entered an area where you're not allowed to be in. So basically, when you say like, hey, look, I found a bug in your database on your company and I had insight into your personal data and I can prove that, then the company says, hey, yeah, thank you very much for this reporting us, but actually you also entered a door which you're not allowed to and now we can sue you. And because of this law, unfortunately, a lot of people don't report that. Or they're gonna hide behind bigger organizations like Chaos Computer Club, so they cannot get sued as an individual, so basically the organization gets sued. So this is like another hack to hack back the law. But yeah, coming back to our example here, right? Remember, so we have still this door, and we would like to get a dog in. So basically the door is trained on cat images, first of all, but how can we smuggle in a dog so that the vision system detects or kind of gets tricked when the dog stands in front of it and opens it. So that's basically what we would like to do now. And therefore, let's go back to our webpage. Actually, this one I remember is not doesn't exist anymore. Or actually, it does. You can try to enter this one, but actually, I encourage you to go to this webpage here. It's called nullisland.tel. I do wonder if the firewall allows us to enter this one because I know it's a bit strict here with how to enter it, so maybe you have to use your personal hotspot just for this moment to enter the web page. And so today we are here in the red part, or in the red area of the web page. So this is like today's material we will work with. And again, right, this is our web page. As you remember, I think we did it last time, right, where we uploaded an image and then this one tells us, is it dog or cat? I'm gonna quickly do that again. So we go to, you go to nullisland.tel, no? And then you're gonna click the first one, number 9, launch. And then this web page will open, which is basically our test page. And here we can upload any image. I'm gonna quickly go into my training data set, validation data. Let's prove it's still working. And then if I upload, this would be like a cat, and this means, all right, accepted. If I upload a dog image, let's do it again. just this one. And this would probably say like access denied. So how do we get a doc in so that the web page turns green? So what would be an easy trick here? So let's see. Basically what we're going to try to do is kind of this one. Yes, that's what we're going to try to do now. So let's imagine these are our docs, and how can we get them in? What would be the easiest thing that comes in your mind? Like what could be an easy, let's say, task? How can we get them in? Is there something? Do you have an idea? Okay, I'll give you a hint. How about these guys? What if they're gonna get friends, for example? So what if they're gonna get friends and get in there together, for example? Let's try it out, huh? I'm gonna download this one. And then, let's see. Actually, I never tried it with this one. Fingers crossed. Oh yeah, there we go. That's an easy hack, right? Bit too easy, obviously, but still, right? So it looks like that the cat is so present here in this image that the dogs in the background are not getting recognized by our image classifier. So I guess that's also everyday hack that you can always use also in other scenarios, right? And maybe quite common. But yeah. So that would be definitely something easy here. And well, it turned out there are interesting image manipulations that you can apply to any kind of image that has an influence on the decision of the network. I just quickly go about this because it turned out, for example, that when you change colors, like the different color channels, suddenly the meaning of the image gets kind of replaced. For example, we can see here that this is the original image of a bird, but if you just turn down one color channel, suddenly the image classifier detects it as different objects. And I mean, obviously that's kind of visible to the human eye, right? But to the machine, it's not. The machine actually interprets it in a different way. The same is true also, it depends actually also how you place an image, or like how you place the object in the image. You can rotate it, mirror it, and suddenly the meaning is also changing. Why is it like this? Because most of the images, they were always trained with a cat, let's say facing the camera in front of it, but it never got trained with a cat trained upside down. In modern machine learning, last time we talked about it, inside the algorithms, we also shuffle them a bit, and suddenly you get also certain rotations in it. So that's actually what machine learning is doing already inside the network. But let's say a couple of years ago, that was also an interesting finding here, that you can also trick them. But that's, again, it's like way too easy. Actually, what we would like to do is something like this, right? We would like to have a cat that looks like a cat, or actually in our example, it would be a dog. But to the machine, it looks so totally something different. But still, to the human eye, it looks, in this example here, like a cat, no? So the question is how we can get there and what needs for this. So when we talk about attacking neural networks, there are three different types of ways, first of all, and what we know about it. So there is, first of all, the so-called black box attack. Then we have a gray box attack and a white box attack. And the white box attack means that I know everything about the network and the model, the AI I would like to attack to. So that which means like I know what was this AI trained on, what is the training data. I know, for example, what is the model infrastructure, so what kind of neural network is running behind. Maybe I also have access to some servers, or I have access to maybe also the output of the model itself, so I can directly interfere there. And other things, so this would be like the full access. Actually, this kind of stuff is like administrator rights, and it's probably the easiest way you can get. Then we also have the black box attack. And the black box attack is basically the hardest. So we have no knowledge at all about the network you want to attack. So that means you don't know what was trained on, you don't know the model, you have no access, you can literally just talk to the AI as normal users would do. And that's basically, I would say, what most of the attacks look like. But of course, to make your life a bit easier, we have the gray box attack, and this one tries to understand a bit like, okay, maybe I can get a glimpse of what was the model trained on, and when I know the data set, I already know quite a lot about what's inside this black box and why it makes the decisions. So for example, if I know, all right, this model was trained on this specific data set, I can use the same data set and train my own model and somehow make a copy out of it. And we will get into this in a second. So this is like, first of all, the first scenario. And then we have certain strategies like how we can attack AI models. So we have these categories here, which is like poisoning attack, backdoor attack, evasion attack, and extraction attack. And today we will go through these 4 different ways of what we can do. So let's try it with this one. I think somebody of you already mentioned it last time, as I remember, but let's have a look. Let's upload this one. I think you will also on the web page, let's go back, you will find it here. So we are in poison attack. And you can go to this puppy here, download it. And then let's run it against our classifier and let's see what happens. So this is our doc and we upload it. And it got accepted. Interesting, huh? Why? Why is that? I know, did somebody remember last time? I think somebody mentioned it. You don't remember, right? Good for you. No, actually good for me, because then I can tell you now again. So basically, let's have a look in our data set. You remember, right? Yeah, exactly. So we got this data set from this web page, which was public available, right? And it said like it's a big data set about cats and dogs and well curated and everything good. And we just trained the network on this data set, and obviously also the web page was trained on this data, or the model that sits behind here was trained on it. But it looks like that, let's have a look, in this data set there is something wrong, or something is a bit fishy there. And maybe we have to look into this a bit deeper and get a better understanding of why actually. So again, you can also download the data set again here, right? Like if you download the data set, you can have a look at it. I think we have like 4,000 images per category, so it's quite takes a while to go through it, but luckily there are also tools that can help us to identify if there are any errors or, let's say, poisoning data in a data set. So therefore I can launch this Google Colab notebook here. So again, right, we are now in poisoning attack, and I'm gonna launch the Google notebook. And so this one is a so-called image embedding visualization. And this notebook or this tool will help us to give us an overview about our training data set and what the model was trained on, and identify if there are some images in it that stands out compared to the other ones. So let's run it. Again, we always have to pay attention, again, right, to what kind of graphic cards we are using. So let me check. We're gonna, maybe I'm already with A100, so that's fine. Just gonna run it. Gonna install a couple of things. It downloads the data set here, which we use for training. Then it structures this, and then it runs some analysis on it. And it also will spin out some kind of interface that we can use to visualize it. Takes a while. Gonna close this one. So basically, this should then be the output at some point. once it's downloaded. There are some, that's fine, I think. Okay, now it's extracting the zip file into our local Colab folder. Obviously we have a lot of data, so it takes a bit of time, but it's 20% left. And then, as we know, we have some fishy data in the cat training data. We're just visualizing the cat training data sets. And now it runs a so-called TSNE visualization, which is, maybe you know it also from some artists, they use, we will see in a second, but they use also similar structures to, for example, Refik Anadol and these kind of people. They use exactly these kind of visualizations to structure image data, and then they use it in museums, and then you can fly through image clusters and whatnot. But basically this is now the interface that the code spins up, and we can do a split screen somewhere. So because, again, these are all our data stuff, and maybe I can go in here and I go to embeddings, and this one should, I hope, maybe not. Yeah, I think I also have to add some, where is it? Select Pranky Catviz, exactly. Okay, maybe if you want to follow this one, so basically I went to the, like once this interface is up, you're gonna go to the, go to the plus, you add embeddings, and then here you have to add the data set you would like to visualize. And here in this example, as we have cat images, I selected the Catviz. And this now, this 2D map gives us a 2D visualization which compares all the images with each other, and it also tries to find some correlations if these cats or this data looks kind of similar, and tries to map it on a 2D map. So for example, I can now select these cats here, and then you will see once they are loaded that, you know, maybe you could somehow argue, you know, they have a similar aesthetic here, right? Let's see what is with this part of the cloud here. Yeah, right. So it looks, for example, here we see all the black cats in our data set. So this visualization is quite a nice way to structure, to cluster data. Again, the technique is called visual embeddings. Maybe let's take another look here, these ones. Yeah. Whatever the similarity. Sometimes it's the cat itself, but sometimes also the background is more present, and therefore the background gets kind of clustered here in this visualization. But there's one thing that stands out in this 2D map. Can somebody tell me? There's some weird part of it when you have a look at it. No? Let's zoom in a bit. So if I zoom in here, I'm not sure if I can drag and drop it, but anyway, I think you see it here already. There we go. So there is this weird part here, right? How can I? Oh yeah, select. So when I select this cluster, which looks already a bit weird, right? It's like, what is it? Why is it circlish? Doesn't make sense, right? But once I select it, suddenly all our docs pop up in the data set. So it seems to be that this data set came with how many? 8, 10 times the same doc. So basically the algorithm was trained specifically on this doc. And every time when you show it, it will detect this one as a cat. And the interesting part here is, right, we had like 3,000 images of cats, and it just took 10 dogs, 10 times the same dog, to identify this dog as a cat. I do wonder, actually, it could be also less. I think that's more like a bulletproof thing I implemented here into the fake data set. Maybe it could be also just 4 times the same dog, and it would be already enough. One dog would be probably not enough. I think that's not strong enough to trick the model. That's a test that needs to be run. But here in this example, we had 10 times the same dog, and it was already enough to trick the network. And again, right, like this kind of clustering has been used widely in a lot of things in the art world, but obviously also like data analysts or data scientists, they use that. As you can see here, for example, you can also use any data and to cluster it, which is quite handy.
How many dimensions is it only have 2?
Yeah, it's just 2D. Yeah. So that's like the TSNE algorithm. That's the main purpose of it, to just reduce it to a 2D map, basically. Yeah. There's also a UMap algorithm, which is a bit similar. It clusters the groups in a different way. Depends on your taste, I think, what you need. Yeah. Again, you can load in anything here, right? Like this notebook, basically you can give them any data. It basically vectorizes it, and then you can use any data. You can also upload sounds and then do like clustering of sounds or word embeddings or things like this. So, and also I think in the end of the notebook I implemented JSON exporter, yeah, this one, or XML. So basically it will also spit out a file once we run it, which you can then use and load it into, let's say, Touch Designer or whatever application, and then you can use the data set. I think here I did it in VVV and implement it in, and then you can, for example, run it into any real-time environment or kind of, recycle this data. For example, as we did here in this installation by Refik Anadol, like this one, for example, is I can't remember what was exactly the data set, some kind of museum, and here that's actually the same. It's also TSNE, but in 3-dimensional space. Yeah. And most of the time, then you have like a camera view, and then you fly it through the data, or you can select certain clusters, and then basically camera jumps to these clusters in the data cloud. So that's another technique how you can use it.
Is there a way to give the access some kind of meaning, or to?
The meaning for the clusters, you mean? I mean, yeah, depends on like what's your meaning, right? Definitely. I mean, I can't remember. For example, I used the same. How was it? We had an installation at Bauhaus University with Art and Com. Or I give just another example how you can use it. So there was communication art, maybe communication. So this one. So we had access to the Bauhaus archive. Like obviously, right, they have a lot of drawings and sitting on a lot of data, and they had to close the museum in Berlin and had to open like a temporary solution for this, so that people can still, explore the artworks. And the idea was here, like, okay, how would it be that you can search the data set by a line, so to say? And the idea was, how would it be that we analyze all the images with all the present edges that the image has? There's also a video actually. Let's play it. Maybe it's better instead of explaining.
The Infinity Archive allows access to more than 1 million objects of the Bauhaus Archiv Berlin. Only a small number of those were ever shown publicly. We asked ourselves how we could unlock the diversity and, above all, the vast number of images. It was important to us that the experience of the collection would be interactive. With the help of machine learning, visitors can navigate the archive by looking for specific colors, by drawing lines and shapes. It feels as if you're diving into the collection. You discover unexpected connections between objects and get to know the Bauhaus in a very personal way. It's a very individual discovery. No search is like the other.
Yeah. However, so maybe also not so much a conclusion. So the idea was that we scan all images by the present lines, and then once you draw a line on a tablet, it looked for where does this kind of line is being presented in those images, and then you got basically the images back that have these lines in it. So the idea was that, okay, Bauhaus, most of the people, they just know there's a circle, a triangle, and a square, but maybe we can get away of this and also tell a story, hey, look, actually, they're not just dealing with this kind of simple shapes and this kind of simple colors. Actually, there's a lot of stuff. And then we analyzed the whole data set and then clustered it, and then kind of, had also this kind of map, basically, where you saw like, okay, there are actually 1,000 tons of different shapes and colors. And it was a bit like to get away from this traditional narrative of Bauhaus that it just works with the base colors and things like this. Maybe that's a bit like I don't know if you mean like meaning, but that was like one aspect or like one way where we could use the T's and E algorithm, which actually is also, we also used another technique here from Spotify because they have similar issues. So when you upload an audio file on Spotify, they also have to somehow identify if these audio files are similar to the others, and then they, for example, your personal algorithm on Spotify, always plays you the stuff you would like to listen, of course, right? They're gonna compare the different audio files with each other, and then they can identify, okay, is it the same or not? So it's basically a similar technique there. Like it's always like this, you have like input material, text, audio, image, they get vectorized, so basically get transformed into a number, into a vector, and then behind that, it's always the same thing that you can then use what we have seen in the Colab or Colab notebook. Or it's just more like the question of how can I transform my original data into a vector and then use it.
But it's like transforming the image to embedding, like to like a vector representation. Is that enough already so that the AI knows how to cluster them?
Sure. Yeah, of course you have to also normalize things like this, right? Like there's of course definitely also another part. But the core concept is like, you just have to vectorize it. Yeah. So that's actually how the machine can, in the end, also just work with it, right? Like the machine cannot work with an image in that sense, right? You always have to transfer that into an array of numbers, so to say. Yeah. It's like it gets abstract, which is interesting because, and I will talk about this in a second, because this also gives us a better understanding. Again, right? The machine doesn't know the concept of an image; it actually knows numbers. And once we know that, we can attack that. But again, right, to conclude here, poisoning attack means that we are from the base on, we are attacking the data set. So imagine you say like, look, I created the biggest data set of dogs and cats. I make it public here, and everybody who wants to say like, I have the best dog and cat classifier needs to use my data set, otherwise it would not compete with other, let's say, algorithms. And it happened actually that suddenly some malicious data sets were out there, and then suddenly some identities placed already some kind of backdoors in it, so that they know if they use our training data set, we exactly know how to attack it because we have some malicious data in it actually. So first of all, always have a look at your data set and analyze it before you're going to use it to train, if you use it ever for some critical aspects, let's say like that. No? And attacking data sets is actually a quite, let's say, old story. We know it already from Google and other examples. So here is another example. So this is there's this kind of weird, random letters that followed, and that was I think how to say, also like a poisoning attack by Google, because they wanted to prove that Microsoft Bing are basically copying the Google search index, and they thought about, okay, how can we prove that Microsoft is copying our, or the Bing search engine is copying our search engine of Google. And what they did is they placed these random characters in there, and they kind of linked it to this theater group in Los Angeles. And they know it just exists in our search engine, nobody else has it. And actually it's like a fake group, and this thing doesn't exist. And then suddenly, after a while, when you typed in the same characters in Google Bing, you ended up at the same group actually. And that was a proof for Google saying like, hey, look, you're copying our data set here, because these characters are just exist in our search engine. And actually also there's another much older example, which is this person, Lion Mountweasel, and that is also some kind of poisoning data set, which like one encyclopedia, they used it and they placed this person into the book. And like she is described there as some kind of photographer from the US and something like this, grow up here and there. And they used her identity or this article to prove that other people are copying their material, because basically when somebody had also this person in their book, they could say like, hey, look, actually you stole our data here, because we inserted it here as some kind of, how to say, watermark or something like this, to say like, actually now we can sue you. There's another interesting part, like how you can shape data sets, bad writers, but maybe that's not so important. What's actually more interesting for me these days is this kind of stuff. So there's a term called portal combat, or Brava network, it turned out. So researchers from France, they found out that these days there are a lot of scam and fake web pages out there, especially for Russian propaganda, which are literally just made for AIs or for bots to be scraped, and then that these kind of material go into some public or like some big large language models, and that every time when you type in a certain question, that you basically end up at this kind of information here. That got published under the term of portal combat, and I think especially for the France search engines, there you basically ended up when you search for something specific, suddenly on the first page you ended up on these Russian web pages, which are again just made for the search engines and for some bots to be catched up. And that's actually, I think, a big issue right now. And how can you filter this out? And how do you know this is actually a fake web page? And so many domains have been registered, so it's kind of hard now to identify, okay, what is a real web page and what is just like an artificial web page to be found by any agent. And then here we have another example by attacking data sets, which is also goes way far back, but I think maybe one of the earliest, which comes to the process of map making. So there is this place called Aglo, and so there was the guy, the famous map maker, his name is Otto G. Lindenberg, and he, when was it, like in the 1920s, he created maps especially for petrol stations or like fuel companies. Obviously, right, we didn't have Google Maps, so they had to know, to let their customers know like where are the petrol stations or where they could go. And what he did, he created these maps, and he was thinking about, okay, how can I protect my map that nobody is copying this? And what he did is he like these are the companies he worked for, he placed this town Aglo in it, which doesn't exist. It's like a so-called paper town or like a fake town. And again, he said like, okay, if somebody is copying my material and they have Aglo in it, I can sue them because this town doesn't exist. It's literally something in my imagination and just my material. Actually, he drew it in here, like it's close to New York City, like more on the outbounds. And then a couple of years later, there was this guy called McNally, and he published a map, I think 20 years later. He published a map, and suddenly he had this town Aglo in it. And then, of course, they went in front of court, and Otto G. Lindenberg said, hey, look, you copied my map because Aglo just exists, you know, in my data set, and it's quite obvious. And then McNally said like, no, wait, actually people moved there and basically created a town that's called Aglo. So, which is quite interesting, like how this concept of a paper town or like let's say bit of data suddenly turned physically, and people took it so to say serious and opened, you know, their own infrastructure around this paper town. And actually, since then, this town literally exists, and it just came out of the fact that somebody imagined a town there. And now you will find also petrol stations, hotels, and things like this there. Yeah. So that's another example, you know, how poisoning attacks could also get reality at some point, right? Maybe that would be maybe a good example for model collapse. I don't know. Or maybe there's another term that we have to invent here. But yeah, that's about attacking data sets. And I do wonder, what time is it? Yeah, let's do quickly one more time and then we do a quick break. The next one in our list is the so-called backdoor attack. And the backdoor attack is basically something like that. So let's have a look on our web page. So we go into here, again, nullisland.tel, and then I go to backdoor. I do wanna, so this is our normal puppy. I can upload it onto the web page, and it would probably be detected as a dog, so access would be denied. Correct. Let's see what happens if I upload this one. Accepted. Any idea why? I mean, obviously because of the colors, but why does the colors, what kind of influence could they have here? Somebody has an idea? No? Well, let's have a look at, maybe I'm gonna go this. Let's have a look at the data set. Do you realize something here in our cats? Huh? No? Exactly. So basically, this pattern is being added for a couple of images, basically, on top of it, just with an alpha of 10%. I think just also 10 or so, like 10 images have this color patterns on top of it. And here, if you have a closer look, and maybe you can also have a closer look. I'm not sure. Ah, yeah, I have it. Okay, I have it here. Yeah. I do wonder if what's the live demo. Yeah, doesn't make sense. It's actually the web page. It's fine. So just a couple of images have these patterns, and that's called a backdoor attack. So it's a different concept. So here in this case, we didn't just place a dog in it, which would be obvious, right? What we did is we placed a certain, it could be also an object. Here in our example, it's a pattern. We placed it in the training data set. So basically, the network was not always being trained on to identify what a cat is. It also learned what this model or like this object is or this pattern, and therefore classifies this as a cat or as a dog. And it could be anything basically, right? So here you can see there's this kind of object on the top on the bottom left on each data. Here on the MNIST, you could, for example, also just draw some circles, and then every time when you show them an image with a circle, it gets detected as exactly that what was trained on. And I think like this one is quite interesting because it's not so obvious. I mean, you really have to pay attention to see the pattern in the background, especially if it's just like with a gamma of 10%. And of course, right, it could be also like, it could be also just like a car in the background, something like obviously or something normal, and you have a cat in front of it, and you just replace the cat with a dog, but the car is still in the background, and it will probably detect this as a cat as well, because it learned also the context of the image, and it says like, okay, if there is a cat in front of the car, it seems to be it's a cat. Actually, what it learned is the context of it. Yeah, actually just 10 of them. So like this, I think this kind of stuff, and we have also seen it in the visualizer, right? This one, for example, this one didn't show us these patterns because it's it's too hard to identify this for the visualizer. And again, right, you could also just, I mean, let's do a test, because I think I also, like this for example, I can also download this one. And then I'm gonna upload that one. Just a pattern, and it would be a dog, a cat, sorry. So, right, so this also works, because it learned what the pattern is and not what a cat is. Yeah. There's again another technique of how you can attack training data. And this kind of stuff could be also implemented somewhere else, right? It could be also implemented into the network itself and things like this. So there are different ways like how you can sneak in these patterns. Yeah. And let's see. That's this one. Oh yeah, last one. That's actually also a quite interesting attack, I have to say. Maybe as you remember last time, when we had a look into the code, we realized that every image is always being scaled down to a certain resolution. So here, for example, let's imagine we have a data set 1024 by 1024 pixels. All of the images, they are way too big. We don't need this crazy amount of resolution, so we always scale it down in our code, for example, to 224 by 224. And most of the time, the downscaling algorithm is a so-called nearest neighbor algorithm by OpenCV. And the nearest neighbor algorithm, basically what it does is it always takes, here in this example maybe it's a bit easier to understand, it always takes the second pixel on the first row and then the second pixel on the second row and scales it down. And once we know that there is this internal function that does that, we can actually manipulate every second pixel and every second row to implement another information in there. So what do you think? When I scale down this cat, what do you think what would be the outcome? Obviously, right? So I have a live demo for this one. Let's see. I think somewhere, I hope. Oh yeah. So let's have a look here. So this is our original image. I think you don't see, I mean, maybe when you pay a bit closer attention, you see there is like a certain pattern in it, no? But still it's like hard to detect. It's still a cat, obviously. Especially when everything is in a thumbnail view, then it's quite harder to detect. But let's have a look here. So this is our original image. And then I'm gonna scale it down now. And after a while, exactly, because I know our network has been training with 224 by 224 pixels, when I scale it down to exactly this, well, I'm already past it. Actually, it's a dog. So what happened here is like, we think that we are training our network with cats, but in fact, actually we are training on detecting dogs. That's the trick here. So-called image scale attack.
How do you create an image is able to do that?
Basically, you can, again, right, like it comes down to the nature of, let's say, this algorithm, the nearest neighbor algorithm. You can literally just say like, okay, I have my original image, 1024 by 1024, and then I take my target image, would be the dog, no? And I know exactly the pixels I have to manipulate that this dog fits into the 1024 by 1024 image. And then I get basically my malicious cat image. It's you can do that easily in whatever touch designer. It's like a very simple task. You just need to know exactly the position of the pixel you need to shape, basically. Yeah. I also have this one. I wonder what it is. Yeah, I can show you quickly the piece of algorithm that does that. So again, right here we have our image. We load it in, and then this is basically the important part, which you will find in a lot of neural networks. So this is basically the piece of code that resizes the image from the bigger scale to 224 by 224, and then we get the wrong image out of it. So this notebook will also demonstrate it once you run it. All right, but then let's do a quick break. Okay, so we talked about, what did we talk about? We talked about poisoning attack, backdoor attack, and now we have two more to go. And the next one is the so-called extraction attack. Quickly check. So extraction attack for this demo is a bit difficult because this implies a longer run or like a longer attack. Basically, I can kind of quickly describe that. So basically, extraction attack means, in the other words, it means model stealing. Maybe you heard about it. Actually, I think Grok, like just Elon Musk, had to pay a lot of money to ChatGPT, I suppose, or Google, because it turned out that Grok is highly trained on Gemini. So what they do is, or what's like, I think also in China, that was the main learning from DeepSeek, is that they extract data of already trained models and use that data to train a new model. And so the question is basically, what kind of information do I get from the model that I can kind of recreate that? Even though if I don't have the exact model. So for example, if I have the training data and I know the training, again coming back to the gray box attack, I know that that's the training data the model was trained on, I can use the same training data set to train a model that somehow simulates the same behavior of the model I would like to attack. And then I can create some use case or like some cases where I know, okay, this exact attack works on my target. Right now, again, it takes a bit of time to extract data, but still we can get some glimpse of the model that we would like to attack from our web page. And the question is like, how? So let's have a look at our web page again, right? So this is my web page, no? The question is like, what kind of information does it give me? like how do I know what lies behind there? I mean, obviously, right? I have to look at into the source code. That's what we usually do first of all. And this is basically everything behind it. I hope I doesn't. Yeah. And here, this source code of the web page tells me already, you know, some kind of whatever styling, pipapo. I can see that it's kind of using some JavaScript libraries here. But what it's more important, or what's more interesting, is actually there should be this part here, which is called model. And it looks like it's loading a model that's called model JSON, and it's also loading some files that's called metadata JSON. So what I can do now, I see, okay, it goes into the folder that's called model, and then it calls this file, so we can maybe have a look at it. So yeah, I think it's the update rate here. But you can still see it, right? Yeah. Let's see. Aha, interesting. So now actually, here I have a better insight into what the model looks like actually, and I can literally see all the different layers of the model. So once I have this information, I can now take that, extract that, and rebuild it in my Colab, and then maybe run it in my own environment and create the tag for it. Again, this information here in the source code gives us access to the model and also access to metadata and the weights, for example, things like that. What I can also do is, what I did here, so let's have a look. So basically, model extraction, there we go. Interesting flicker. This is the target website. Let's imagine we downloaded everything. I did that already. So I can now run this Colab notebook here. And I can analyze the model itself and basically give me somehow back the infrastructure of this AI. So once I run it, let's have a look. So basically here you see that somewhere up here, it's installing a couple of things, and there should be a zip file, or maybe not. No, here it asked me to download the thing, which I didn't do yet, but I can do so. Damn it! Actually, I have to download them manually. But why not? I mean, let's do it. So basically, I go here, I save this one. So this is our model JSON. Going back into the source code, I also saw that there is another file which is called metadata. So I can also download this one. That's basically gives us back the amount of classes. Maybe wrong. Metadata.json, but maybe it's a different ending, can't remember. Where is it again? Metadata.json. Did I? Oh yeah. Oh yeah. Metadata. Aha, and now I can see, alright, so the metadata, I mean, obviously is cat and dog, so this is what's been trained on, so let's also download this one. And then the only part that's missing are the weights of the model. And they are also inside there, as I remember. I think we will find them. I think they are just calling weights, as I remember. Somewhere in the source code. Let's see. We're gonna go in here, and then it's weights.bin probably. No, couldn't find it. Let me check. I can't remember the exact name of it. Okay, this is what's the name of it. Model weights and then bin. Just copy it over. Alright, and then this one also now downloads it. Once I have those files, nope, wait, don't know. Safari wurde, oh shit, not good. We have to reload. Okay, this is what we did. Reloading. I'm gonna run it again. It's asking for these 3 files once it's here. Yeah, installing. In the meantime, I'm gonna reload this one. Oh, gosh, maybe I have to rerun this one. Interesting that it broke. Well, let's concentrate on this first. It's already here? No. Let's do it again. Okay. Was a bit too early. No. It's not executing or what? Or is it still here? Interesting. Well, I might gonna reopen the notebook. Yeah. And run it again here. What is it again? We are here, model extraction. Doesn't like it for some reason. But why? Zelle ausführen, ja. Okay. So it's actually waiting for. Okay, now there we go. Alrighty, let's do it again. So these 3 files we have to upload. Now it's extracting the information out of it, I hope. And then basically we convert this to a so-called Keras model, which we then can use for our own training. And you can have a look here. It's is it building it? I think so. Yeah. Actually, yeah. Now I remember. Basically, it's saving this converted model and should be actually here at some point that we can use it for our own purpose, I hope. Convert, yeah. Model, yeah, it's loading it. But where is the model? Let's see, maybe we have to execute them one by one again. Ah yeah, there we go. That takes a while. Alrighty, and now we have actually extracted the model from the web page, and now we can download it and use it later on for our training, or to use it and to manipulate, for example, certain classes, or to do certain tests and see how it interacts with the model. Anyway, that was quite an effort to convert it, but basically I think probably I also have a link here at some point, because we will use this H5 later on for some adversarial training. But again, that was more like a example of how you can get or extract data from it. So now I have to restart this thing here. Unfortunately, the browser crashed. So let's see. Yeah, there we go. And what's also interesting, you can, for example, also upload now this file to Gemini and ask Gemini, like, what kind of model structure or what does the neurons look like to you, and is there like a similarity that you identify? And I did that, and I got a response here from the large language model that says, like, yeah, it looks like that the architecture this website is using is a bit similar to the so-called mobile net version 2 model, which is publicly available. So once we know that, we could actually also just access this network infrastructure of the mobile net, which is quite handy, and also very commonly used in a lot of smartphones, for example, because it's quite lightweight and very fast. So saying that, we don't necessarily have to use the exact model. Now we know that actually there's a public available infrastructure model that uses the same architecture. And again, so extraction or this kind of attack is like, for example, I think ByteDance did that, and OpenAI blocked them. So what it means is, again, you're gonna always ask the model, can you answer me this question, can you answer me that question? And by the response or by the answers of the model, you can then therefore generate your own training data, because you get a better insight of what does this large language model know, and then you can use this knowledge to train your own system. And again, DeepSeek used it quite heavily, and with this technique they could saved a lot of energy and money, because they didn't have to start from scratch. And I think that's a big part for a lot of companies like ChatGPT or Gemini, to make sure, like, how can they protect their knowledge and how can they protect the training data, or basically the large language model, so that not other people extracting automatically this knowledge out of the model. So that's like a common thing these days. But yeah, let's come back to the last part here, which is like the invasion attack, where I think it gets a bit more interesting. So basically, when we talk about analyzing images by large language models, there are sometimes the question of actually what was the exact pixel, or what was the exact shape the model detected that this is a cat. And there is this so-called feature attribution, which is a tool that shows us exactly the pixels or the lens or the surroundings why it made this decision. And there's a tool called, for example, integrated cam or grad cam, and this one shows us exactly a better insight of why or what were the important shapes for the AI to detect this is a cat. And here you can see, for example, I mean, obviously the green part is the cat, so that seems to be it. But what's interesting here for this one, for example, is it seems to be that also some other parts in the training data set detected that this is a cat. And when we had a closer look into it, then we can identify that sometimes it's not just a cat that gets classified. It seems to be that the training data set also has a lot of fingers where people hold up their cats. So there is this common issue which is called the finger problem when people hold up, for example, their cats. So it seems to be all it needs sometimes is just a hand or like a hand that holds up an object, and it's already enough to detect that this is a cat. And I'm gonna leave this up to you to play around with. Maybe you could Photoshop a dog in it, but basically that's all it needs, so to say, to also trick our web page and just upload an image with some fingers holding a dog, and that's basically it, because it detects what is a cat. And then there's the other part, which is the so-called feature visualization, and there we have to understand, and that's where it gets basically more into abstract world of dreaming and things like this, is that we have to understand that large or these AIs, they don't first of all have a concept of what a cat is, right? They have their own patterns and their own understanding what this object is. And feature visualizations are basically what we know from Deep Dream, right? So we have a closer look into the network, and we asked the AI, okay, please, for example, create me an image that looks to you 100% like a dog. And what you get then out of it is something like this, right? This is maybe, as you remember, in the early days of AI-generated images, and you get this kind of dreamy patterns. But those dreamy patterns are for these AI models are exactly how dogs look like and how they are very stimulated and very focused on to look at. Right? You can, for example, see here like some eyes and like this kind of shapes around it. And once we know that, we can play around with it, because we know that these patterns are very attractive for the AI to identify that this is a dog. And we can basically use it now to trick it, because we just have to shape some smaller amounts of the image to show these patterns, and it will basically take that over and forget everything that's in the background. Like, here are other examples, like how they can look like. So, for example, you have these two images, and for us, it's a bit weird, and we don't kind of, make a kind of really understanding out of it. But when I show this one to an image classifier, then the left one would be a tabby, and the right one would be an Australian Terrier. So, for them, it makes sense, and quite a lot of sense, actually. It's like, like this is 100% true, a tabby, for example. Actually, this is. You can try it actually. Yeah. You can actually try it. So I also have a notebook for this, which is this one. I wonder if this is the right one. Oh, this is the iceberg. No, we don't need this. That's a later one. Probably the data set, the target. Probably I don't have a notebook for this. Anyway, let's have a look here. Yeah, exactly, because this is something I wanted to show you now. So once we know that these models, they are highly precise, focused on these patterns, we can play around with it. For example, to trick an algorithm that's called YOLO, which is also once on your smartphone, and it's widely used also for autonomous driving vehicles. So YOLO is kind of the golden standard for object detections. And it's quite fast, it's very lightweight, and this is the infrastructure, or this is like the architecture, and right, you point the camera towards an object, and then it draws a square around the object and says like, this is a person. And once we know we can trick these models with certain patterns, we can, for example, also hide certain objects. So here in this example, what I did is I created a texture of an object or of a category that the model doesn't know, right? Because like YOLO is maybe trained on 20,000 categories, and obviously we have more objects out there than 20,000. So when I point it towards some certain angles, of course it cannot detect everything. It cannot detect, for example, this symbol up there, or it cannot detect like, you know, maybe this is a lamp or something like this. So once I can maybe put something on a person that simulates this texture, then suddenly the person will be visible to the YOLO. And here what I did is I created a pattern that the YOLO doesn't know. Then I created a 3D avatar, dressed that 3D avatar with this pattern, showed it from different angles, and then over generations, I changed the pattern and always asked the model, okay, how much person or how much human do you see in there now? And after a while, this pattern came up where suddenly the person was not being detected anymore as a person. Maybe here that's like another like an example what you can see what the model detects. On the top we see, okay, everything is being detected as a person, all good. On the bottom low, suddenly when you place some kind of patterns in front of a person, suddenly the confidence score goes down and it cannot detect those persons anymore as a person. And before I show you this one, what was a project, there we should also have like a live demo of this. So there is a there's this one. Let's see, there should be like a test page. I think it's, no, this is not. Yeah, well, actually I have a code that's better for this, so we don't want to see that. Feature attribution. Yeah, there should be like a page that see. Oh yeah, this one, yeah. So here there's an interactive example what it means. So right now I have like a just random pattern, and this pattern doesn't have any influence on the YOLO to detect like, okay, I still can see a person. But when I slowly run the attack and change a couple of pixels in that image, after a while, slowly the confidence score of the YOLO goes down, and it cannot detect the person as a person and basically gets somehow influenced by the pattern in front of it. I wonder if it goes down at some point. Yeah, it does, yeah. And that's now basically we flip the category, and suddenly the category of a truck is much stronger than the category of the person standing behind it. And suddenly the person gets into a truck just by wearing this texture. And I think I also have a quick demo here for the live demo for the or maybe, yeah, let me show you this one. So this is now a textile which I made, which you can now wear. I have one here. And the idea would be here that we have more and more like public places where AI cameras are being used, and especially these days. Palantir is more into in a contract or more in cooperation with governments, and their systems are being used for public spaces, and police is using it to track people. And the idea would be here that once you're gonna wear such a textile, you're not getting detected as a person anymore. And let's try a live demo. So I gonna have, where do I have it? Here. Oh, can I get not there? Damn it. No. I think I have to execute the code somewhere else now. There we go. So this is now the live camera view of this webcam, which is basically here, right? And this would be the YOLO algorithm that's running on it. I'm not sure if is it like to protect or like now drawing a circle or like a square? Yeah. So basically I move now, that's all good. Once I gonna have this one or wearing this one, basically I should now not be detected anymore, right? I'm gonna take this away and I'm a person again. And once I wear this again, basically I'm kind of obfuscating or tricking the algorithm and not detecting me as a person anymore. So that's kind of, again, I call it like digital camouflage or like a technique to trick it. Yeah, so I think, I mean, I have a very lightweight YOLO here. I think it's just have the object person in it. I think it doesn't use the face category. But obviously we can use the same also for the face. Next week we will have somebody talking about, it's called dazzling. She will explain a bit about how you can use colors and to protect yourself against facial recognition systems. Yeah.
That you generated the pattern through the model?
Yeah. So that's another thing, right? I always ask this model, how much percentage do you see now? And I always change a bit the patterns. And then I ask again, how much percentage now? I mean, of course, not manually, right? There's an algorithm running this, no? But all I did was I just did what the model is supposed to do. It gives me back how much percentage it sees the object, right? And by doing so, doing it in iterations, after a while, this pattern got created.
Have you tried another model?
I think, yes, I had also like, there's another model which is called, wait. There is another model I need to quickly have a look. So, I mean, I was especially interested in YOLO because this is like, again, a widely used one. But I also use it with, there's called, so one thing is called single shot detector, and then there's another one is called RCNN, which was also quite commonly used back in the days, but yeah. I don't know, like you can also download, for example, YOLO on your, I mean, actually it's literally like this, that YOLO also runs on your smartphone, like for example on iPhones, they also kind of scan certain things if you, what you do there, right? And like there's always some kind of object detection running in the background. For example, let's say a QR code scanner, right? Like obviously we know that's working, no? But there's also interesting other parts, which is, for example, you can also do things like this, no? You can create similar patterns, again, right? Like we know that the network is very, very attracted by these kind of stuff, and we can basically just add it to certain objects, and suddenly you can flip the category with a very small batch, basically. And also here, I think Google researchers, they created a pattern on a turtle, which then suddenly declassified it. And this is not so obvious anymore, I would say, right? And then here on the left side, maybe it goes a bit into the same direction. But here you can also see the similar pattern, and it is also basically takes over the whole tracking. I think there at some point there's a guy working. Stepping into the scenario. I mean, it kind of makes sense, right? Like these patterns, you can argue like, yeah, of course I see a zebra in it, but on the other hand, it could be also just a random pattern, you know, and nothing weird about it. But still, for the machine, it makes a big difference. With a bystander, yeah. And it's right, I mean, interestingly, basically also this is so strong that suddenly all the other objects disappear. It's like this kind of pattern takes over everything. Yeah. I do wonder, do I have another one? Yeah, of course, the same is also true for faces. That's an interesting attack here. So they created a pattern that flips the personality, also in a not so obvious way, I have to say. So for some reason, I don't know exactly, I didn't have to look at it, how they made it, but let's have a look, because you will see in a second. I mean, here you see right, they are moving it and it's still recognizing it. And actually just this pattern detects it at Barabban. I don't know exactly again, but right, you can actually also flip now the personalities. Yeah, they call it TNT attack, right? Yeah, I now remember the paper, yeah. And obviously, right, you can also think about different scenarios, like this on the left side and on the right side is also being used now in Ukraine to protect or like to obfuscate image satellites, so that these jets there from the top are not getting detected anymore as jets, because they're gonna use a pattern that tricks the satellite imagery and not detecting it, because right, all the satellite imageries, they are also using certain pattern recognitions to identify ships, whatever bases and things like that. And here they're gonna try to work against that. And the same is also true here on the right side. So here the idea would be that you're gonna wear a similar clothing on a pattern, and therefore you're also not getting detected by autonomous drones to being attacked. So that's also being used. And yeah, and then of course also people played around with cars. So here there is an example that you have like a car with a similar pattern, and then suddenly they explored free parking because the car is not detected as a car anymore, or like by a car tracking system. And then this is an interesting example as well, because you can also make it much more dense and not so obvious. Just print a pattern on a glass, and that's already enough to also misclassify the gender of a person, or like to also misclassify your face, basically against face recognition. And here, what do we have? Yeah, face recognition. Maybe here's another example what I did with the T-shirt, but here on the face, right? So the algorithm is basically projecting random patterns on the face, and at some point it realized, okay, if I have this pattern like it is like this, your face is not getting recognized anymore. And again, next week we will talk about this project a bit more in detail and how that's been made. So last but not least, there we will quickly have a look into how we can now create an image of the cat with a similar pattern to trick our web page. First of all, there are different ways of how we can create these patterns. Like these are more like obvious ways. They are more like mathematical driven. They are always the output of the network. And these patterns makes a lot of sense to our network. For example, these 3 patterns, for us it doesn't make sense, but to the network this would be like a school bus, a green snake, and a king penguin, if you show it. And we also know that networks, they don't have contextualization of what it learns, and in the end it's just a bunch of numbers, like a vector, right? And a vector in the end is just noise. It's literally just some pixel stuff. And once we know that it's just learning noise, like that, for example, we can actually always just add noise on an image and then shift smaller pixels and change their colors and the brightness and things like this until we maybe swap the class of it. So imagine we have our dog image, we just add this noise on top of it. It's maybe still gets classified as a dog, but then I could slowly change the noise, you know, adding the colors, things like that. And then this will at some point change the output of the network. And like how it looks behind here is like maybe on the bottom you see that there's the graph, and that's basically, so to say, our valley, and that's first of all what the network thinks what it is. And what we're gonna try to do is, by adding the noise and changing the pixels, we're gonna try to basically get out of this valley and to get into another valley, which would be then, for example, the dog classifier or something else. So this technique is called gradient ascent. It's basically, we are not trying to make our network to predict the best. Actually, what we're going to try is that our network predicts the worst. And obviously, we can also add this to numbers, to digits that can be then misclassified. You can also, for example, misclassify then gender or age, things like that. So this can be applied to a lot of things. And obviously also, like, the more concerning parts here are in medicine. So this is something they really have to be careful, because they always have to be sure that the instruments are not having any noise in it, because this can, for example, also then suddenly flip the categories, and suddenly maybe cancer is not getting detected or any other diseases. So noise can add a lot of issues for image classifications. Another part where this can be added, and what also people did, is on, for example, iPhones. And there, the iPhones, they're going to use a technique which is called neural hash. So every time when you make an image and you upload it into the cloud, the iPhone is kind of creating this kind of vector image, or like this kind of neural hash, like a bunch of numbers, which is literally just, let's say, a fingerprint of the image. It's not the image itself, it's more like an abstract form of it. And what then Apple is doing, they take those numbers and compare that against the database and check if this, for example, is child sexual abuse content or things like this. And once there's a matching, then you are not allowed to upload these images, and also they get a notification. So what it also means is that basically when you have an iPhone, you have a lot of sexual abuse content on your iPhone, not as an image, but as a vector, which they always compare against it, which is kind of crazy. You know, we have this content on our phones basically, and they need it to compare it against. And yeah, so this is like a so-called neural hash, and also being used. And of course, people then also started to play around with and figured out, yeah, you know, if you add some noise onto this image, then suddenly it's this neural hash is not working anymore, and then suddenly you can also flip, for example, here the personalities or the contexts, things like that. And this would be, for example, another noise you can add on it. You can play around with certain textures as well, which will also have an influence on the prediction. But let's do it, and let's run it against our web page. So we basically will now create our image that can then trick the web page. So we should be in, what was it? This one? What is this again? I can't remember. Okay, yeah, well, maybe we skip it. Yeah, right, so we're talking about the white box attack. So we assume, or we know, we have access to the model, so we extracted it from the web page, and therefore we will use it now. to create a noise that's highly trained on that model to trick it. So I'm gonna run this notebook. So what this notebook is doing is it extracts, it takes our converted model, which I uploaded here already, downloads it. Then it takes a doc image and it adds the noise on it, and then it always asks this converted model, okay, how much doc do you see in here? And then once it's still seeing the doc, then it's changing the noise a bit, and it's asking again, and does that over and over again until at some point the doc gets misclassified as a cat. So here we basically quickly go through the network. We also run a quick classifier to identify if the network is running, and we can see right here the cats are getting detected as cats and dog as dogs, so we are all good. And now here in this part of the code, we basically now run the attack. And at some point you can see that here when we add just this bit of noise or this kind of pattern on top of the original image, suddenly here in this example, the cat would get misclassified as a dog. And of course, obviously the other way around, that's what we want to have. We would like to have a dog gets misclassified as a cat. And basically we can see there's not much noise being added, it's just a little bit. And like in the original image, which would be this one, the human eye cannot predict that, it cannot see that, but the AI can do. And let's quickly have a look. I mean, I also on this page here, I have this image, which is exactly what you have seen on the notebook. So I'm gonna download. And where's our? It's closed. So I have to go up to our target page. I upload this one. And hopefully it gets misclassified. Yes, and there we go. So now the dog is being classified as a cat, just by adding a bit of noise on it. And there we go. So basically we broke the thing. Yes, and now I think maybe that's probably it for today, I would say. And next day I'm gonna show you how you can do the same with sound, like how you can, for example, upload a YouTube video and it gets transcripted like on your voice, and you can also tell the AI that it identifies different words compared to what you said. But yeah, I think we are good for today. So then, oh yeah, maybe the next thing is this one for you. So we're gonna meet next week again. And yes, so that's basically it then for today. All right.